Then we introduce another method for reduction of order, which is a better choice instead of just a times independent t. So a better choice, where instead of times t, we times alpha t plus b. So we times this linear function. We have y2 t will be equals to lambda t plus b y1 t. And we know our y1 alpha t plus b times y1 t, and we know our y1 t is x times e to the mu t. Okay, and that will be alpha t times x e to the mu t plus b x e to the mu t. And we assume this bx is a z function, so that is alpha t x e to the mu t plus a z function here, e to the mu t. Okay, so this is a better choice for represent our y2. Then what is our y2 prime? So y2 prime will be equals to alpha x e to the mu t plus alpha mu t x e to the mu t plus mu z times e to the mu t. So that is just the differentiate t with this expression. Then what is y2 prime also equals to? Equals to ay2, right? And ay2 will be a times alpha t x e to the mu t plus a times z times e to the mu t. And you know that this ax equals to lambda x, and lambda equals to mu. So that it is mu alpha t x e to the mu t plus a z e to the mu t. Okay. Then you know that this equation 1 and equation 2 are equal because they are all equals to y2 prime. So y equals 2 equals y2 prime. That means all the right side of the equation should be equals to each other. So alpha x e to the mu t plus alpha mu t x e to the mu t plus mu z e to the mu t is equals to mu alpha t x e to the mu t plus a z e to the mu t. Okay? And you see that this term and this term are equals to each other, so we cancel out. Then we left this part and this part equals to the right side, az e to the mu t. Okay? So we can rewrite alpha x e to the mu t plus mu z e to the mu t equals to a z e to the mu t. And since e to the mu t won't be 0, so we can cancel out. Okay. Then what we can get in the end is alpha x plus mu z is equals to a z. Okay. And in order to solve your alpha and z function, what you can get is alpha x equals to a minus mu I times z. Okay. And here, what you know, you already know what is I, that is identity matrix. What is mu is your solved repeated root are lambda 1, 2. That is the repeated eigenvalue, basically. This A is your initial problem site, that is the coefficient matrices. You know the X already because that is the eigenvalues associated with the eigenvector associated with the eigenvalue mu. What you don't know is this alpha and the z, and you can basically set alpha equals to 1. That is the simplest one. then you can solve Z. Okay, and you can solve Z. So that is how you can get repeat a second linear independent solutions based on reduction of order using a better choice. Okay.